going to talk about the difference between Cauchy's theorem and Cauchy's integral theorem and when you might use each. So Cauchy's theorem says that if you have an open set and f is holomorphic, so the integrand is holomorphic on G, that's the key thing, then it doesn't really matter, right, if you here you have G and it should be an open set, so imagine that dashed line. It says that if you have this thing and this thing, gamma 1 and gamma 2, and as long as these are homotopic to each other, it says that that the integral over this one is the same as the integral over that one, as long as it's homotopic in a very nice way. That is, you have continuous second partials. So how do you use this? You normally use this if you have, you know, some big G where everything works nicely. What you normally want to do is you want to take, if this is maybe a gamma, and of course f has to be holomorphic, the integrand f has to be holomorphic in all of G. If you want to take the integral over here, typically what you'll want to do is make it holomorphic to a circle, because it's very easy to parameterize a circle and figure out what that is. So if you can figure out, so Cauchy's theorem says that if you could figure out what the integral of this very holomorphic function is over this green thing, that's going to be exactly the same as this red thing, as long as these two are homotopic in a very nice way with continuous second partials. And ideally, what you do is you take the smallest circle possible. So oftentimes, you will create a homotopy where if you want to, you know, find the integral over here, and you have a very nice holomorphic function, you might be able to take it all the way down to a point. So that would mean that the integral over the point would be 0, because there's basically nothing to take the integral over, and the integral of the red stuff would be equal to the integral over the green stuff, which means that they're both going to be equal to 0. Now, you won't always be able to do that. For instance, if here's your G, if G is just the inside of here, kind of like this donut thing, then if you want to take the integral over here, you might be, the best you might be able to do is to be able to just take it over the circle, if these are homotopic. You can't actually shrink it down to a point. So that's Cauchy's theorem. You need to have the integrand be holomorphic on all of G. But that doesn't always happen. Maybe the integrand is not holomorphic over all of G. Maybe, for instance, you have, like the simplest example is, what if you have a nice holomorphic function? This is holomorphic on G, but then you're going to divide through by this point, where so we're going to look at integrals of this thing, where the numerator is holomorphic, but this causes the integrand not to be holomorphic, causes non-holomorphic at G. So for instance, you might have, maybe this is entire, but maybe you want to integrate over this circle where W is on the inside. So this W messes everything up. So you won't be able to use Cauchy's theorem because you're going to be integrating over something where it's not holomorphic. Right? This has to be holomorphic everywhere. Here the integrand is not holomorphic everywhere. It's not holomorphic at W. So, and let's be even very specific. Let's say that this is like 2 plus 2i. Well, Cauchy's integral theorem says, okay, so in the really nice case where the integrand is completely holomorphic, the answer is just basically what you get with a circle or a point even. What this says is if you have, let's make this very specific, 2 plus 2i, as long as you meet the conditions, this is holomorphic, etc., you've got kind of a simple region counterclockwise. So this is just going to be equal to 2 pi I, as long as you're going around counterclockwise, times f of 2 plus 2i, the bad point. That's how you do it.